All right, I think we're live here. So yesterday, I realized about 15 minutes into the stream, I realized this after the stream, that the microphone had completely stopped working. Someone actually commented on Twitch. My first ever comment said, "Your microphone isn't working," which was nice to know that actually there's some random person watching this. I had no idea. I had no marketing or anything done to try to get people to actually watch this. This is kind of a self-indulgent endeavor at this point, just learning about live streaming, content creation, and linear algebra. But that was interesting. And so I just spent about 20 minutes debugging it. I realized at the end of that my Shure MV7 Plus microphone, if you touch it, it goes on mute. So when I gave it a little nudge to adjust it, I think I muted it inadvertently. And here we are. But now I've figured out how to do mute lock. ChatGPT helped me figure out all these things. You can actually see my Shure MV7 Plus troubleshooting right here. And we should be good to go. So without further ado, let's jump into day 4 of linear algebra. I'm going to scroll to the very top to get the curriculum here. And lesson 4 is going to be bases and dimensions. It says that I should be able to comprehend what a basis of a vector space is: a linearly independent set of vectors that spans the space. So we're getting some of that terminology that I saw on ChatGPT o1 Pro last time that gave me a little bit of pause. And then also it says to find a basis for a given subspace, find a basis for the column space or null space of a specific matrix, and define dimension of a vector space as the number of vectors in any basis, and use this to describe, it didn't transcribe the math format, but the planes, lines, etc., and more abstract spaces. All right. I'm ready for lesson 4. Actually, I had a good thing here. I'll start this and then have this highlighted. So explain more what the columns of a matrix mean and how they relate to vectors. This whole jump from matrices to vectors has been a little bit shaky, so I want to ask what the deal is with those, basically. So the columns of a matrix, if you have a matrix A such that R m times n, it has n columns, each with m entries. So you write it like this. This is a lot of tricky formatting. I can see where this would throw a lot of people off, myself included. This is a little tricky to decipher, but it seems like the columns in a matrix are literally just vectors in Rm. What is Rm? What does this R symbol mean? What does the M mean? I'm gonna ask it that. Let this load. What does this R symbol mean? And what does M mean? So I'm going to do this lesson. I'm going to try to get through it pretty quickly with ChatGPT 4.0, and then I want to try a different model, probably o1. And then I'm also, if I have time within the hour, going to spend a few minutes just going on to Grok, I think would be best, and asking it for some quick marketing tips, things that can improve the reach of my channel on TikTok, YouTube, and Twitch, to see if there's anything I can do on that end. You know, creating the content, learning is the main point here, but I want to learn about how to promote these things too. Ideally get more of you guys to join and follow in this journey, learn all kinds of things with AI, get better at using all these tools to get learning superpowers, etc. So what does Rm mean? R, the fancy symbol R, means the set of real numbers. So this is the R2 is the set of all 2D vectors. And this is how they're writing vectors now, I guess, is as a vertical column in a matrix. And a vector, from my understanding, is just a magnitude and a direction. So the magnitude you find by Pythagorean theorem, basically. X squared plus y squared, square root that, or x squared plus y squared plus z squared, square root that. And then the direction you find by looking at this x value, y value, and z value, or whatever it is. So Rm is all vectors with m entries, this however many coordinates, so we can have more than 3 dimensions here, where each entry is a real number. Just saying you're working in an m-dimensional real space. All right, that's helpful. So I'm going to write that down as my first note of the day here. My Face ID. So R M, you're working in an M-dimensional real space. What is a real space? I assume it just means there's no imaginary numbers. There's probably a deeper understanding of it than that, but that works for now. So in the context of a matrix, if A is an M by N matrix, we always go rows by columns. Each column of A is a vector in R, let's see what this means, in an M-dimensional real space. That's what Rm means. Each column of A is a vector in M-dimensional real space. Okay, this is starting to click a little bit. So for instance, this is a 3 by 2 matrix, 3 rows, 2 columns. Each column has 3 components. So it's a subspace of a 3-dimensional space, R3. And each of these is a vector within this. Okay. Cool. All right, that makes sense. I'm ready for lesson 4 above. Now we wait. I'm going to ask O1 to do the same thing, by the way, here. So we're going O1 instead of O1 Pro. I'm learning linear algebra. Give me a lesson for this. All right, so core concepts. But I need to know what it means for a set of vectors to form a basis. So this is a key term, basis. Find a basis for the subspaces like the column space or null space of a matrix. So I think I've written these key terms down before, but I need to know what a column space is as well as a null space. It feels like linear algebra has a lot more key terms and terminology than other math classes, which is interesting. I'm going to build some little tool that can help me with these key terms, keeping track of them since my notes are a little bit all over the place. But I'll do that later. Maybe if I have time again too, I could probably make it in 10 minutes with cursor and AI coding it. So maybe I'll have time to do that if we can get through this quickly. So I need to define and compute the dimensions in a vector space. So I need to figure out what that means to a vector space. Use these ideas to describe lines, planes, the set, an n-dimensional space, and more abstract subspaces. So I need to also understand what a vector space is and a subspace. Obviously, a subspace sounds like it's a space within a space, but I'd like to see if there's more formal understandings of that I can get. So what is a basis? A basis for a vector space is a set of vectors that are linearly independent and span the space. Okay. Said differently, a basis is the minimal set of building blocks from which you can build everything in the space via linear combinations. Okay, so that's what spanning the space means. Linearly independent means they're separate lines. So we're working in a two-dimensional space, a real two-dimensional space. These two vectors form a basis for R2 because they are linearly dependent and their span covers all of the two-dimensional space. That makes sense. An x vector going horizontally and a y vector going vertically will cover all of this space. Any vector in R2 can be written as x times vector 1 plus y times vector 2. These don't form a basis because they're linearly dependent. They're the same line. The only difference is this one goes 1 in the x direction and this one goes 2 in the x direction, but they're both going to be horizontal like this, right? So, delete that. What is a dimension? The dimension of a vector space is the number of vectors in any basis for that space. Man, they're saying words that I know in English, but they have a very specific meaning in linear algebra that's a little bit tricky to grasp. So we have dimension. I'm just checking. Yeah, my microphone still works. This is positive. Do I have a chat going? Yeah. Well, I doubt anyone's going to watch since there's no way anyone would find this, but let's see. So we have two independent vectors. Any non-zero vector. Wait, sorry, I skipped ahead here. So all bases for a given space, bases for a given space have the same number of vectors. So this is a two-dimensional vector. A line is a one-dimensional vector. An example basis would be two independent vectors. If you get two vectors, they can form this whole two-dimensional space. You have a line in the 3D space. That's one-dimensional. An example basis would be any non-zero vector on the line. A plane in three-dimensional space is two-dimensional. Yeah. The null space of matrix A is going to be the number of dimensions n minus the rank of A. Basis comes from phi variable vectors. Okay, so this is confusing. I'm going to screenshot it. The column space of matrix A is the set of all vectors. In other words, all linear combinations of the columns. Okay, so the pivot columns, all right. This is all very abstract and tricky to see. I'm going to be much better when I have examples and some multiple choice questions or problems that I can solve to test my understanding. The null space is all solutions where something times the vector equals 0. All right, I have no idea what they're talking about here. So let's see this. Is this a basis for the set of real numbers in two-dimensional space? Are they linearly independent? Yes. So if we try solving to see if they can equal 0, it leads to a trivial solution, so they are linearly independent. Their span is two-dimensional. They form the basis of R2. Okay. Let's see. In example 1, how do I know their span is 2D? We'll keep going here. Find a basis for the column space of this. So I want to row reduce to get this second row set up. So I'm going to pivot. The pivot columns are just 1 and 3 when I do that, because you'll see I do R2 minus 2R1 makes this 0, 0, 0. And so let's see here. The pivot columns are 1 and 3. Why is 2 not a pivot column? Because it doesn't have a 1 in it. All right. So the basis for column space, columns 1 and 3 of the original matrix. One, 2, 0, 3, 6, 1. I have no idea how they got this. So I'm going to have to ask some questions here. How did you get that basis for the column space? Also, why are 1 and 3 the pivot columns? Column 1, column 3. Couldn't I multiply the top row by 1/2 and make it 0.5, 1, 1.5, and make that into, and make it so that column 2 All right, already spamming it with questions. It's annoying that the questions are just going to line up and I'm going to have to keep scrolling up and down. This is, again, a UI issue with using just raw ChatGPT to learn here as your tutor, but it's going to get better in time, and it's not unmanageable. All right, find a basis for the null space of this. So I don't know what the null space means necessarily. Face ID here again. So here's this. We row reduce it. Okay, this is pretty basic because the bottom one becomes 0, 0, 0. I'm going to need two free variables, x2 and x3. So then it becomes x2 is s and x3 is t. Let me go and try example 2. I'm going to just write it out, and maybe I can make sense of it even before I look at the answer. So example 2 here is saying that I'll just write the row reduced form here. 1, 2, 3, 0, 0, 0, 0, 0, 1 is going to be the same thing as x plus 2. Oh no, there's not really an equation here, so that's a little tricky for me. All right, I think I understand how they got this. How they set it equal to 0, 0, 0, though. Let's look at example 2. So how do we know this is a two-dimensional span? Oh, if it's not a line, it's a two-dimensional span, basically. Because they're linearly independent. They both live in this two-dimensional plane. And there are two vectors, the maximum number of linearly independent vectors possible in R2. That means their span is the whole plane. Cool. V1 says go right and up and also independently. Steep diagonal. So any point and the real numbers in two-dimensional space is reachable by some combination of these two directions. That doesn't seem to make sense to me because they're just two lines. There's a lot of points that won't be on the other of those two lines. In R2, one vector spans a line, two dependent vectors is just a line, two independent vectors is a span of all R2. I mean, I get that. It's easy to solve. I just, again, conceptually don't understand why two independent vectors spans all of R2. Maybe my understanding of span is different. Because I feel like if you're trying to just get infinite x's or y's, then one line would be enough. But let's see here. Perform Gaussian elimination. It's nice how ChatGPT encourages these questions, I feel. I know it's just a large language model talking to me, but I feel a little smug that I asked a good question according to them. Maybe they say it to everyone, but still, it's nice. So the original matrix here, row reduce, yeah, that's clear. This is all clear. The first non-zero entry in row 1 is column 1. The first non-zero entry in row 3 is column 3. I guess I just don't fully understand why row echelon form. The whole concept of row echelon form is a little interesting here. I guess I need to just let that gel a little more. Why that is so crucial and why you can't mix all the columns or mix all the rows around and get a different version of this. But all right. What is the basis for the column space taken for the original? So the pivot columns of the original matrix form a basis for the column space. This is one of those key phrases I'm just going to copy here. So we have pivot positions using the row reduced matrix, but we take the actual basis vectors from the original columns. 1, 2. We take the actual basis vectors from the original columns. Oh, so that's where we get the 1, 2, 0 and 3, 6, 1 from up top here. Okay. So I want to ask why that's the case. Got a lot of whys here. Why? Pivot positions are determined uniquely by the structure of the matrix. They do not depend on your row operations. So you can scale rows, swap rows, etc., but the set of pivot positions after row echelon form is uniquely determined. Even if you scale row 1, this doesn't make column 2 a pivot column. Yeah, it doesn't. It just changes the numbers. The leftmost column with a pivot is still column 1. A column that contains the first non-zero entry. Since this isn't 0, it wouldn't be. Okay. So we got the big picture summary. Row reduce A to row echelon form to find pivot positions. Identify pivot columns in row echelon form. And it's annoying that it keeps going to my screensaver here. Oh, I should go on Do Not Disturb. That's probably a good idea. All right. This is interesting. Man, phenomenal question. I must be asking some good questions. All I said was why. But yeah, we row reduce a matrix A to find pivot columns. This helps us see which columns are linearly independent. Then we go back and so which columns, which are vectors, are not the same lines, are linearly independent. Then we go back and take the basis vectors from the original matrix A, not the reduced one. Man, I will say, as a math tutor, it's really good for me, I feel like, to be learning some math and be thoroughly confused. This is just, again, good empathy for my students when I'm trying to explain something. I think it's clear. And they're just going, but why? And there's still the big but why here. It's linear algebra. Why does this matter? We haven't even gotten into, maybe slightly into how it's used in machine learning or physics. Why does this type of math exist? How does it matter in the real world? I think that's, there's theory and then there's practice. So I want to get there eventually, but I'm in no rush. Right now, I'm just trying to understand this strange language that they're trying to teach me. So we row reduce a matrix to find pivot columns. We go back and take the basis vectors from the original matrix, not the reduced one. Why do we use the original columns for the basis of the column space instead of the cleaned up ones from the row reduced matrix? Man, I'll just tell you right now, I'm just thinking there's going to be such a good online learning platform built out of AI stuff eventually once they get this. If you could just have the lesson plan stay as a constant and have me sort of branch off into all the details, asking questions and everything, use AI to analyze the depth of my questions, assess how well I understand it, all of these, it's going to be insane, but it's not going to look like just an ongoing chat. It's going to have a different interface. But yeah, it's going to be amazing. So let's see. When we use the original columns for the basis of the column space, instead of the cleaned up ones, let's see. The column space is defined using the original matrix. Column space of matrix A is so that's what col means. A span of the columns of A. So it's the set of all the linear combinations of the original columns of A. Let's see. So the average transaction at the IB that Amex people spend is 294. Here, let's see. And the average transaction at the shore is 322. I told her it's not very helpful because we don't know so 2 or 4 people. Row operations do not preserve column space. Why can't we use the reduced columns? Okay, sorry, I'm getting all lost here. When you row reduce a matrix, you're applying row operations, which changes the rows and therefore the values of the columns, but row operations do not preserve column space. So I'm wondering why that's the case. Why we can't use the reduced columns. You row reduce it to some matrix are not the same linear combinations as the columns of the original. They may not even span the same subspace. Therefore, using them could be the wrong basis for the wrong space. You're studying a band sound. You apply a filter to track to identify which instruments are playing. If you want to recreate the actual song, you have to use the original instruments, not the filtered signals. So row reduction helps you analyze structure, but to represent the column space, you need the original materials. Let's see. Okay. 1 second. So yeah, let me see a counter example. While it's generating that, I'm going to scroll back up to the lesson, make sure I'm still doing well with time. Find a basis for the null space of this. Oh, so the null space is where it's equal to 0. That's why they were able to set it to equal to 0 here. Okay. So I'll need to explain more of what a null space is here, but interesting. I need to go to settings and look at this. Five minutes? No, I'm on 15 minutes. So I'd set, all right, I got all this. The basis for the null space is this. Okay. While it's loading all this, I'm going to jump into practice problems. Again, it's a little annoying with ChatGPT. You have to jump around the chat, but not a big deal. Didn't really end up doing example 2. That's fine. So problem 1. Do the vectors form a basis for R for the 3-dimensional real space? Why or why not? I can just tell you right now, no, because they are not linearly independent. They're the same line here, right? Find a basis for the column space of this. Okay, so I'm just going to go to problem 2 since problem 1 was super easy. Find a basis for the column space of this. A equals 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to need help with this. I can just tell you right now. I think, well, let's go back to the example problem. Maybe I can figure it out from that. Find a basis for the column space. You row reduce to figure out. Okay, so you row reduce first. So I'm going to go ahead and row reduce by going R2 becomes R2 minus 4R1, which gives me 0, -3, -6. Then row 3 becomes row 3 minus 7R1. So that's going to be 0. 8 minus 14 is -6, -12. So the new matrix is going to go 1, 2, 3, 0, -3, -6, 0, -6, -12. And I need to get rid of this -6 now, so I'm going to go R3 is R3 minus 2R2. This new R2 should work because I have 0 there. So negative 6 minus 2 times negative 6 is 0. So it's going to go 0, 0. Oh, and then we have another 0 here. Is that right? Negative 12 minus 2 times negative 6 is 0. Okay. So the row echelon form is going to go 1, 2, 3, 0, negative 3, negative 6, 0, negative 6, negative 12. Oh, whoops, sorry. 0, 0, 0 for the last one. I gotta stop saying sorry when I make a mistake. It's such an overused word, sorry. I don't know why. Sorry should mean something, not just I made a mistake while I'm talking to myself. So, with this, we need to find now the pivot columns were 1 and 3 in the initial one. Now the pivot columns are 1 and 2. So the basis for the column space, let's see if this is right. Basis for the column space is going to be 1, 4, 7. This is a classic example of where I can solve this problem. 1, 4, 7. Hopefully I've got it right. 2, 5, 8. Because 3 is not a pivot column. But I really don't know what this means. The basis, the column space, these are all very abstract things. Maybe I'll have to watch a YouTube video. All right. So I want to see a counterexample, a matrix whose reduced form has different columns, but it has different columns, but a different column space. So we have this 1, 2, 2, 4, 3, 6. And the column 2 is 2 times column 1. Yep. So the two columns are linearly independent. The column space is the span of 1, 2, 3. Did it say span up above for that, by the way? In that example? No. Anyways. So if I row reduce A, I get this. So the column 2 is 2, 0, 0, and 1, 0, 0. This is the reduced matrix. The second column of the reduced matrix is that, but the original column space was that. Can I solve where this reduced matrix, this vector, contains the span of 1, 2, 3? In other words, can I solve some constant times 1, 2, 3 equals that? No. There's a contradiction. The second column of a reduced matrix. All right. The column space of the reduced. So I'm still confused on column space, I guess. But let's first go and have it check my work on the practice problem number 2 and 1 above. And meanwhile, I'll see if I can do problem number 3. Man, it's hard to find this. Dimension of the null space of this. So in the example problem, to find the null space, I need to set it equal to 0. I think I can do this. Prob 3. So we have this right here. What I need to do first is row reduce. So initially it was 1, 1, 1, 0, 1, 1. Is that already row reduced? I kind of feel like it is. Let's say that it is row reduced. Then I go x plus y. I guess I'll use the same syntax as they do. X sub 1 plus x sub 2 plus x sub 3 equals 0. So x sub 1 equals negative 2, x sub 2 minus x sub 3. Say let here. And then from there, I get that the basis for the null space, so I get the x vector equals s okay. So it's negative 1, 1, 0 plus t negative 1. That's because I have this for the x sub 1. The x sub 2 is 1 here. Sorry, the x sub 2 is 0. The x sub 3 is 1. Since that's t. Okay, so therefore the basis for the null space would be all right. Let's see how that goes. Would you look at that? I was right for problem 2. Nice. You row reduce. Column 3 has no pivot here. Take the basis vectors from the original. Yeah. Problem 1, yep, linearly dependent. Now to problem 3. I'm going to take a quick look here. So I may need a visual to understand what it means for vectors to span a vector space still. So it's defining basis again for me. This is useful reading another definition. So I didn't get problem 3 correct, it would appear. Nice, my microphone's still working. Haha. So for problem 3 right here, yeah, it was totally different. So I'm going to walk through their answer. So the dimension of the null space, I need to set up the homogeneous system. So you write out that equation. Pivot variables were x1 and x2. Yeah. Free variable is x3. So that's my issue, is I made x1 the free variable. So I'm going to just draw a light cross through this. So I want to say instead that x3 equals let's see, x2 plus x3 equals 0. That's what I get from the top row here, or from the second row. So x sub 3 equals negative x sub 2. Aha, this is clever. So then from the first equation, I get x sub 1 plus x sub 2 plus x sub 3. And I can do some substitution here. X sub 3 is negative x2. So x sub 1 plus x sub 2 plus negative x sub 2 equals 0. So x sub 1 equals 0. X sub 2 equals negative t, and x sub 3 equals t. Yeah, that makes sense. Okay. And so the general solution looks like that. Got it. The null space is a line through the origin. It has dimension 1. So basis for the null space. All right. Well, since this is my own class, that's all right if I have to pause for a second. I have to run to the bathroom. I'll be right back in 30 seconds. All right, we're back. So, all right. The dimension of the null space is 1. All right, yeah, let's go. You know, if you want to practice finding null space bases or connect this to, yes. I don't think I formally learned rank nullity theorem or how to find null spaces. I can just write rank nullity theorem again, so I remember that it's something I need to know. Rank nullity theorem. Oh, yeah. Rank is the number of pivot columns, the dimension of the column space. Nullity, okay. So the number, so n equals 3. That's the number of columns. There's 3 variables. From row reduction, I see that there's a pivot in just column 1 and 2, so its rank is 2. There's 1 free variable, so its nullity is 1. Cool. All right, I got that. Explain column space more. Oh, I get that. It's a subspace spanned by its columns. And I find the pivot columns. And it's only the pivot columns. The why here is I feel like I'm just following an abstract set of steps, which is never great in math because math should completely make sense. But I'm following an abstract set of steps. Like why, for instance, do I only use the pivot columns in order to find the column space? Why is it only the, okay, yeah. So we kind of talked about that earlier. I didn't fully understand their explanation, but of something at least that I can let gel in my head. The null space. Let's see how long this is. All right. Jumping between worlds here. Column space is all the linear combinations of the columns of a matrix. It's a subspace of an m-dimensional space. A space that outputs live in when you multiply the matrix by some x vector. So this is the example. I always like these examples. So here we have 1, 3, 5, 2, 4, 6 as the columns. Those are the two vectors. The column of A is equal to the span. I'm going to ask this again, like, why are columns vectors? Like, why does this matrix form even exist? There's a foundational thing about matrices that I guess I'm still figuring out. I guess matrices represent numbers and positions. All right, so this is the columns space of A is the span of A1 and A2. It's the set of all vectors that can be written as combinations of the two columns. So the column space is the set of all vectors that can map to via A times some x vector. It's basically the range of linear transformations that we get with a x equals 1, y equals 3, z equals 5, that's a vector, and 2, 4, 6 is another vector. So if I were to draw that out, I think it's something like, here's x, y. Excuse me. Excuse me. And z goes like this. So it'd be like one thing going like this, and then another thing going like that. Two lines in this 3D space. Hard to visualize that. So the column space is the set of all vectors that can, and it's the range or image of the linear transformations of A when you go from an n-dimensional space to an m-dimensional space. It's also the output space for that. Why is it useful? That'd be good to know. To solve multiplying a matrix times some vector to equal another vector, you have to ask, is B within the column space? If yes, the system is consistent. If no, there's no solution. So column space tells you which right-hand sides B are solvable. This is totally confusing. So in three-dimensional space, if A has one pivot column, the column space is a line. If it has two pivot columns, it's a plane. If it has three pivot columns, the column space is all of three-dimensional space. So the rank of A tells you the dimension of the column space. All right. Well, I'm going to go back to go to the practice mini quiz now. I think I'm ready to give that a shot. Concept quiz, 10 minutes. What are the two properties that a set of vectors, I'm going to actually X out of that. What are the two properties that a set of vectors must satisfy to be a basis? Linearly independent and same dimensions, or non-zero? True or false, every subspace of n-dimensional space has a unique basis. No, you can have things that are linearly dependent, that are overlapping basically. If a matrix has 4 columns and its rank is 2, what is the dimension of its null space? So if a matrix has 4 columns, rank 2, its null space, oh, that means if its rank is 2, that means that its nullity is 2. I think, does that just mean it's 2? Let's see. Answer these. I'm going to highlight that thing that was confusing above again. Yeah, that. Whoops. Linearly independent. Oh, they span the space. That's the part that doesn't make sense. I guess I want to see an example where they're linearly independent but don't span the space. Every subspace has infinitely many possible bases, but all of them have the same number of vectors. That's what the dimension is. So subspace 1, 0, okay, what does that symbol mean? Is a line. But there's also these bases that will be on that same line. All these are valid bases for the same subspace. So subspace has many bases, but they're all the same size. They all have the same size. Matrix has 4 columns and its rank is 2. What is the dimension of its null space? Its nullity is 2. The null space is 2-dimensional. There are 2 free variables in the homogeneous system. Understand visually more of what null space means. So when you set it equal to 0, here's a concrete example. It already knows what I want. Oh, 1, you're smart. I didn't have time to get into Grok or Perplexity or Claude or Google Gemini or any of the other AIs today, but I want to try those for future lessons still. Just kind of crammed today because I had to troubleshoot my Shure microphone. Wow. Remind learners that the concept of basis and dimension applies beyond an n-dimensional space of real numbers. For instance, the space of polynomials of degree less than or equal to n has dimension n+1 with the standard basis of that. Dimension corresponds to degrees of freedom, or the minimum number of directions needed to describe the space. Many advanced topics, diagonalization, change of basis, inner product spaces depend on understanding basis and dimension. So this does matter. Wow. A basis is a minimal spanning set without redundancy for a vector space. That's why you can't have it be linearly dependent. This makes no sense. Injective 1-to-1 and full rank. I don't know what those mean, so I need to get some more key terms down. Injective 1-to-1 for a transformation and full rank. I know what 1-to-1 means for a function in 2 dimensions. Null space is a line through the origin in 3-dimensional space. So here there's 1 free variable. It's only 1 pivot though. So a line can get flattened to the 0 vector when you multiply by a number. That line is the null space. The null space, it can be a plane as well. Matrix has only 1 pivot. See, I thought this matrix only had 1 pivot, so that's weird. All right, that's all crazy. This is all crazy. Let's preview what the next lesson is going to be about. Matrix multiplication and inverses. Here, 1 sec. Yo, I'll be right out. All right, I got to run in a second. We're wrapping up here. But day 4, success. a lot of key terms. I'm realizing how terminology intensive linear algebra is and the necessity of my getting something. Basically, what I would like is to be able to just copy down a bunch of things that ChatGPT tells me that I don't understand and keep a running list of those so that I can go and review them in the background, gradually have them make sense. So I want to build an app for that today, ideally. I think I could do it in about 30 minutes, like a little Chrome extension. So follow me if you want to check out a little bit of coding as well. I'll show you how I use Cursor and Claude and Gemini and ChatGPT and all that. Actually, I haven't used Gemini. I've just heard that 2.5 Pro is the best one now for coding. I'll probably stick to what I know, Claude 3.7. But regardless, thanks for tuning in. It's been a fun day. And by fun, I mean intense and effortful, and my head's spinning a little bit. But it feels rewarding to post these and to learn and to get better at using ChatGPT and these amazing resources we have to learn about anything, even something as kind of crazy, abstract, complex as linear algebra. So thank you for tuning in. I'll post a short later with some recaps from the lesson and catch you guys soon.